Okay, I'm going to solve the problems on the Introduction to Bayesian Statistics workshop. And already here I've got my answers ready to go. I tried to create a video earlier where I was typing in the answers as I went, and unfortunately my computer glitched out halfway through, so I lost that video. So now I've got the answers ready to go, and we'll see if this works. Okay, suppose I have a box with 3 balls in it. Some of the balls are red and the rest are black. Let n be the parameter that represents the number of red balls in the box. If you reached into the box and the first ball you randomly select is red, then what is the likelihood function for n? Okay, so this situation is about as simple as a probability model can get. You have a random event. You're drawing out a ball. It's either red or black, only 2 possibilities. And of course, the probability that it's red would be n over 3, because it would be n red balls out of 3 balls in the box. So that's our probability for the event that we're actually observing, and that's what becomes the likelihood function. That's how likelihood functions work. If you know the probability of the event that happened, then the likelihood for n given the event that happened is that probability. And now we just think of it as a function of n. Okay, so we're done with the likelihood. It's that simple. There's nothing else to it. By the way, this kind of simple probability model where there's only 2 outcomes and a fixed probability is sometimes called a Bernoulli model, or it's also a binomial distribution with only 1 trial, right? Okay, the second question says, now make a tree diagram assuming that the possible values that n might have are all equally likely, which just basically says we don't have any clue what n is, so we're saying maybe it has an equal chance of being anything from 0 up to 3 red balls in the box. And then we're going to use this tree diagram to talk about the probability of something happening. So first, in the tree diagram, I made 4 branches, one for each of the possible values of n. And then from those, I branched off either red or black. And of course, if there are 0 red balls in the box, then you're guaranteed to draw a black ball from the box. That's why the letter B is here with a 100% chance of taking this path. On the other hand, if there's 1 red, that means there must be 2 black balls left. So there's a 2/3 chance of getting a black ball or a 1/3 chance of getting a red ball, and so on. If it's all 3 red balls, then you're guaranteed to draw a red ball. Okay, and then the way tree diagrams work, of course, is you multiply along the paths to get the final probabilities. So these are the final probabilities for all of the different things that could happen. And then I ask here, I say, find the conditional probability that n equals 3, given that the ball was red. So how do you get a conditional probability? Well, of course, you do the conditional probability formula. You take the probability to get the probability that n is 3, given that you drew a red ball. You find the probability that both things happen, and then you divide by the probability given the probability the ball is red. So we need to find the probability, first of all, that the both things happen. So both would mean that n is 3 and the ball was red. All right, multiply along that path, you get 1/4 is that probability. And then you divide by the probability given. And the given is the probability that you got a red ball. And if you look through the tree diagram here, the ways you can get a red ball, you get a red ball here, that's 1/12 of the time. You get a red ball here, 1/6, and red ball here, 1/4. And of course, 1/12 plus 1/6 plus 1/4 adds up to be about a half. Not about, exactly a half. And so if 1/4 divided by half is a half. All right, so that's our conditional probability. Okay, now it turns out what we just did here, we actually calculated what we call in Bayesian statistics a posterior probability. It's the probability of something being true, n being 3, given a result that we just observed. All right, and in number 3, I say let's calculate the rest of those posterior probabilities for the different possible values of n for 0, 1, and 2 with our given that the ball was red. And I suggest a different approach would be to use this formula, the Bayes theorem formula, which is basically just a way to calculate conditional probabilities if you know the reverse conditional probability. So if you know the probability of B given A, then you can take that and flip it around and work out what the probability of A given B must have been. Now it's basically the same math you were doing with the tree diagram, it's just a different, more algebraic way to think of it. So I've set this up down below here with the 3 different Bayes formula applications. So I've got to do this calculation 3 times, once for k equals 0, once for k equals 1, once for k equals 2. So when k is 0, I'm asking what is the probability that n was 0 given that I saw a red ball. And now, of course, if you think about this, this is obvious. It couldn't possibly have been 0 because if we drew a red ball, then there must have been some red balls in the box. So the number of red balls, n, should have been at least 1. So clearly this is going to have to be 0. Let's see if the formula agrees. So the formula says you take the probability that n equals 0, and that's going back to our original model where we had no idea what n was, and so it was equally likely to be any of the 4 things. So that's a quarter. All right, so I put a quarter in as the first number. And then you take that probability that n is 0 and you multiply it by the probability of getting a red ball given that n is 0. So if n was 0, what's the probability of getting a red ball? Well, it's not possible to get a red ball, so that probability is 0. So then you do 1/4 times 0, and then you divide by the probability of just getting a red ball, which we calculated already was a half. And of course, this times that times they're divided by that is 0. So yeah, it works. The Bayesian formula gives us the right answer there. Okay, when n is 1, you do the same math. Now you have the probability n is 1 is a quarter, the probability of red given n being 1. Well, if n was 1, then the probability you take the red path is a third. So you do a quarter times a third and then divide by half, you get 1/6. And then the last one, you just punch in your numbers, divide by half, you get 1/3. Okay, so we have these. Each one of these is a conditional probability, so we have 4 different conditional probabilities for the different possible values of n, given that we've made this observation that we got a red ball on our first try. And we call this collection of conditional probabilities the posterior distribution. And so if you go over here to the next page, I tell you a little bit about the terminology in Bayesian statistics. So in Bayesian statistics, you start with basically a simple probability model that describes what you know about the situation. And if you don't know anything, a good model often is just a simple uniform distribution saying, I have no idea what n is. It could be any of these possible values. So that's what we call a prior distribution. And then you go do some kind of statistics, like you collect some data, you get a sample, and in your sample you look at what you got, and then you use the likelihood function given what you got to update your data and get this posterior distribution. And the way you do that is we have this really simple formula that basically summarizes what we just did in the last 2 problems. The posterior is always the prior times the likelihood. Now actually the symbol I'm using here is this symbol, which means really it's proportional to, right? And this will come up a lot. The posterior is a probability distribution, so it has all the entries in the probability distribution, all the probabilities have to add up to 1, and that won't always happen when you multiply the prior times the likelihood. But that's okay. Once you do this, then you can just figure out what the total is and then divide by the total to normalize so that you get the right probability distribution. Okay, so with a discrete distribution like this, where there's only 4 possible outcomes, you can just make a table. I've already listed the priors here. We already calculated the likelihood function. Let me scroll back up and show you that again. It was just n over 3. So then for the different possible values of n, the likelihood for 1 would be, oh, I made a mistake here. This should be, let me fix it. It should be 1/3 is n over 3, and it should be 2/3, and it should be 3/3 are my likelihood functions. Sorry, that was my fault. Okay, and then what you do is you do likelihood times the prior. So this is going to be 0 times a quarter is 0, that's right. And then 1/3 times a quarter is 1/12, so that's not right. I can fix it though. And then 2/3 times a quarter is 1/6, so let me fix that. And then finally 3/3 times a quarter, of course, is just a quarter. And when you add all those up, this plus this plus this, the easiest way to add them up is give them a common denominator, so a 1/12. So 1/12 plus 2/12 plus 3/12 makes 6/12, which is the same as 6/12 is 1/2. So there we go. Okay, now unfortunately those numbers didn't come out to be a probability distribution, right, because they didn't add up to 1, but it's easy to fix. If you just take these numbers and then divide by whatever their total is, then that'll make them bigger, right? Dividing by half makes all these twice as big, and then they'll add up to 1, and you will get a probability distribution. And that's what I did on the last column here. That's what we call the posterior distribution. And hey, those are the same numbers we got before. This is just a quick and easy way to take a prior and your likelihood and turn it into a posterior distribution. what the posterior distribution, it tells you basically everything you know about your parameter n given the results you've gotten. So given that we had no idea what n was before we drew a ball out of the box, now that we've seen a red ball, we actually do know something about n. We know it's more likely to be a bigger number, less likely to be a smaller number, and it's definitely not 0. All right, and that's all reflected in the posterior distribution. The whole philosophy of Bayesian statistics is that you take your sample and you use it to update your prior and turn it into a posterior, and then the posterior distribution tells you everything you know about the parameter you're interested in. Okay, so let's do another example, a little more complicated. This is number 5, where I ask you, what if you have a ball with a box with 7 balls now, and you don't know how many of them are red? So you're going to start with a simple uniform prior distribution. This time, I guess, if there's 7 balls, then it could be anywhere from 0 up to 7 of the balls could have been red. And so if we don't have any clue beforehand, then a simple prior distribution would be to say, well, maybe they're all equally likely. Maybe n could be 0 or 1 or 2, all the way up to 7. That's 8 different possibilities. So I guess let's just assume that they all have a 1 in 8 chance of being the correct value of n. And so that's what I used here as my uniform prior, is 1 out of 8. And then to find the posterior, I'm going to need the likelihood function. And when you draw balls out of a box, if you've got a mix of red balls and not red balls, then the number of red balls that you draw out when you take a sample of 3 balls, like you do in this problem, that number has a hypergeometric distribution. And it's been a while since we've done a hypergeometric distribution. We didn't do it this semester at all, I don't think, but we talked about them last semester. So if you don't remember that one, here's where you find it. Go to the Software and Handouts tab, and then if you look on the Discrete Probability Distributions handout from last semester, this thing, then hypergeometric is the distribution you have when you have a population of a size that contains a certain number of successes. So in our case, we have a population of 7 balls, so our n in this hypergeometric geometric distribution notation is 7, and then we have an unknown number of red balls in there, the successes of the red balls. So we have an m, and this is a little confusing because in the workshop I'm using the letter n for this, but on this handout I use the letter m. Okay, so m is n, and n is 7, and then the little n is the sample size, and we drew a sample of 3 balls. Okay, so then the probability mass function, the probability of getting a certain result k, is m choose k, so that would be n choose k in our notation. And then we would have the total population size is 7 minus n over, yes, so the numbers are, I apologize, a little bit confusing. But here's what I got when I put our numbers into this. So we know that k, we actually know what k is, right? We know what happened. We got 2 red balls, so k is 2. We know what little n is, that's 3. And we know what big N is in this notation, it's 7. And the only thing we don't know is the letter M here, which I'm using the letter N for. So our probability mass function is N choose 2 times 7 minus N choose 1, which is like saying we're going to choose 2 red balls from the N that are in there. And then we're going to choose 1 black ball from the leftover 7 minus N balls that aren't red. And then we're going to do that out of all the possible ways you could choose 3 balls from a collection of 7. So that's where this formula is coming from. Okay, now one thing to notice when you do the calculation here of the posterior distribution is that you're doing the prior times the likelihood, but then you don't really care how what the constants are in this formula. You really only care about the important variable stuff, the stuff that depends on n. So you can almost just completely ignore all the constants in the formula. So like this 1/8 is just a constant. It doesn't depend on n, so we can ignore it. And same thing with the 7 choose 3. It doesn't depend on n. We can just ignore it. It's just a constant. So really the only thing that matters is this n choose 2 and then the 7n choose 1. And you can simplify those two formulas. N choose 2 is the same as n times n minus 1 over 2. And 7 minus n choose 1 is just 7 minus n. So you get this really simple formula that is basically our posterior distribution, except that we didn't normalize it. So let's calculate this using some kind of calculator. I'm going to use R because R can do this pretty easily. It automatically does a calculation like this if I want to calculate this for all the different values of n from 0 to 7, then R will automatically vectorize that calculation for me, so it makes it pretty quick and easy. Also, the dividing by 2 is also completely irrelevant. It doesn't really matter, right, because it's a constant. We'll deal with the constants at the end. So the only thing that really matters in my posterior calculation is the posterior will be proportional to n times n minus 1 times 7 minus n. So let me go ahead and pull up R. And so one easy way to do that at home, if you don't have R installed on your computer, is just go over to the Sage cell for a quick R calculations link. Click on that. Pulls up a Sage cell that's already set the language to R, and then I have my values of n are, let me make this really big so you can easily see it. My values for n are anything from 0 to 7, so you can type 0:7, and then what that does is that just creates a vector in R with the numbers 0 through 7. Okay, and then I'm going to want to apply this calculation where I calculate n times n minus 1 times 7 minus n, right? So the first part represents the n choose 2, and the second part represents the 7 minus n choose 1, and I'm ignoring all the constants. And when I evaluate that, I get some pretty big numbers, right? I get 10, 24, 36. These are clearly not probabilities. But how am I going to turn these into probabilities? So the posterior distribution is proportional to these numbers, but these numbers are too big to be probabilities, so we just need to divide these by the total. And so to find the total, I'll just sum these up. So I could say, tell me what the sum of these numbers is, and R will be happy to calculate that for me. And then whatever that is, so it's 140, that's what I'm going to divide these numbers by. So let me get those numbers back, but this time I'm dividing by 140 so that they become the posterior probabilities. So the posterior probabilities, for 0, the probability is 0, right? There's no chance that there could have been 0 red balls in the box. We know that because in the situation what happened was that we drew 3 balls and 2 of them were red. So at least 2 balls in the box had to have been red, so n has to be at least 2. And that's showing up here because the first 2 possible values of n have 0 probability. The next one, n being 3, is possible, but it's not really that likely. It's only 7.1% of the time. The next one, n being, this is 0, 1, 2, 3. The probability that n is 3 is 17.1%. Probability that 4 is 25.7. Probability that 5 is 28.5. No, maybe if I round that, 28.6 would be more accurate. And then about 21.4%. And then finally the last possibility, 7, that can't happen either, because if all 7 balls were red, then I wouldn't have been able to draw that one ball that wasn't red. So that can't happen. This has 0 probability. So now that I've taken a sample and observed what happened in the sample, now I have updated my prior and I have a new posterior distribution. I rounded these numbers and put them in my answer, and here's the table that I got. And so you can see right there, for the different values of n, here are my posterior probabilities for that value being the correct value of the parameter. Okay, so if you recall back when we were doing likelihood functions, we insisted that likelihood functions are not probabilities. But now that we're doing Bayesian statistics, you can turn likelihood functions into probabilities if you have a prior distribution in mind to start with. Then prior times the likelihood is the posterior distribution, and that is a distribution. You can talk about, probabilities now and say, okay, I'm, this sure that n is bigger than 5 or something, and you could say, all right, bigger than 5, well, there's a 21.4% chance that it's bigger than 5. And you can say things like that about your parameter of interest. Okay, again, like with likelihood functions, the math here isn't too terribly complicated, right? It's mostly just basic arithmetic and a little bit of, plugging in formulas. The subtlety, of course, is we're working with stuff that's new and a little bit abstract, so it will take a little bit of getting used to. Good news is we're going to do lots of examples, so as always, if you have any questions about any examples I do, let me know. I will post some homework, hopefully over the weekend, and you can take a look at that too. All right, take care, everybody.